Section 2 is on chiral molecules, and honestly this subject belongs more in an organic chemistry unit, but nevertheless your book puts it in this chapter, so I'm going to cover it here. And so chirality is a chemical occurrence, I guess, in which two molecules can be mirror images of each other, but non-superimposable. And this is visualized by having your hand. If you were to stick your right hand in front of a mirror, this hand right there, the mirror image in green, I'll highlight, would look like your mirror image's left hand, right? So I'll put R for right hand. This would be a left hand, right? If you stick your left hand out in front of you, it would look more like the one in the mirror image, right? Okay, but if I was to take this left hand, you can see that it does not overlap with the right hand at all. They're non-superimposable mirror images. But if you just take your two hands, you can put them together, your pinkies line up, your ring fingers line up, your middle fingers line up, your index fingers line up, your thumbs line up, and for the most part, obviously there's going to be some differences, but for the most part your two hands are identical, assuming you haven't had any crazy accidents to your fingers and such. So they're mirror images of each other, but they're not superimposable. Some molecules can be mirror images of each other and be superimposable. These would not be chiral. So just for clarity's sake, I have a box there and a mirror. The mirror image of that box would be this box. You can see they're the same. Right? So those are mirror images that are superimposable on each other. All right. Pairs of chiral molecules have the same physical properties because they have the same chemical formula, they have the same connectivity of their atoms, but they can have drastically different biochemical properties, and that is because of the way that your enzymes work in your body. So like you probably have all heard of the lock and key model with how proteins work and such. Well, these molecules, if they're something that you're going to interact with in your body, they're going to interact with enzymes ultimately. And since they are different in space, like your left hand and your right hand, one can fit into the lock as a key and the other one wouldn't be able to. And so, for example, there was a drug that used to be given to pregnant women to treat them for morning sickness. It was called thalidomide, and it's a chiral molecule, and it used to be administered as what we would call a racemic mixture. You won't see this in your book anywhere. But a racemic mixture is 50% of each, for now I'll just say mirror image molecule, or chiral molecule, okay? The problem with that is that one of the two molecules treated morning sickness, prevented women from throwing up and all that, or at least alleviated the symptoms of their morning sickness. But the other molecule, the mirror image of that first good one, actually caused very, very, very bad birth defects in babies. It did not help out with the morning sickness either. It literally just is a teratogen, which just mutates growing fetuses. And so that was obviously a huge problem, and once this was found out to be the cause of these birth defects, it was immediately stopped for its use. And now we have the technology to actually separate it and get 100% of the good kind, but it's so well known in what it did that people are afraid to, and so no one's ever going to okay the use of thalidomide again, even if we don't make racemic mixtures of it anymore. Or at least we could make it 100% of the desired compound. So anyways, even though they're the same chemical formulas, same connectivity, same type of bonds and everything, they can have very good or bad and different consequences when we ingest them. Another example is a chemical that has these chirality, where one of the mirror image smells like lemons and another one smells like oranges. I mean, that's not like a huge difference, but they're different nonetheless. The pictures here show two chiral things. You've got the gloves being chiral, you've got your tennis shoes being chiral, but in the center you've got two glasses that are mirror images of each other, but they are achiral because there's literally no difference. If I was to just take the glass on the left and rotate it around, is anything changing? Of course not. If I take the shoe here and I was to rotate it around, it would no longer have the toes at the bottom and the heel at the top. Those could flip and it would look nothing like this at all. It wouldn't be a mirror image of it at that point. Chiral carbon atoms are carbon atoms that are bonded to 4 different groups. And when that happens, we get one form of stereoisomerism. We saw another one with cis-trans isomers in the organic chemistry unit. So if we have a hydrogen and a hydrogen, a methyl and a methyl, that would be trans 2-butene. But if we have this right here, this would be cis 2-butene. All right, those are stereoisomers of each other because they have the same chemical formula, the bonding is the same, the connectivity is the same, just their orientation in space is different. So that's one type of stereoisomerism. What we're going to talk about here, though, specifically are enantiomers. And enantiomers are non-superimposable molecules that contain chiral centers. What you can notice from the alkenes above, these don't have chiral centers because a chiral carbon has 4 different groups bonded to it. When you've got a double bond in it, though, by definition, you have a carbon here. If you have a carbon-carbon double bond, that bond and that bond are the same group. So for this carbon, you've only got 1, 2, and 3 different groups bonded to it, so it is achiral. All right, and so here's where we can actually visualize chirality. What you'll notice in the molecule on the far left here, we have the chemical formula of being CHClBr2. And then we have CHClBr2 on the far right as well. Or I could say right there, actually in the middle. Okay, if I was to rotate the molecule in the middle, counterclockwise or clockwise, it really doesn't matter. You can notice that we get the exact same molecule. So we have the hydrogen above, We've got 2 bromines on the left here, but they're going to end up over on the right, which puts the chlorine over on the left. And you'll notice that if I was to take this molecule on the left and move it over here, they're exactly the same. So what we can tell, or what we can glean from this, is that this central molecule, the carbon, only has 3 different groups and is therefore achiral, or not chiral. On the other hand, with this molecule on the left here, we've got the chemical formula of CHClBrI, which is a ridiculous chemical formula, by the way, but we can see the one to the right of it across the mirror, CHClBrI, same chemical formula, carbons in the center in each case. They're definitely mirror images of each other because you have the chlorines on the same side, back, and in the back portion on the right here, back, and on the left. The iodines are in front on the right there, or I'm sorry, yeah, in front to the right, and then this is in front to the left. The hydrogens are straight across from each other, and the bromines are both to the back side of the molecule. This bromine is on the right, that bromine is on the left, and so they're exact mirror images of each other, right? But if I was to take the molecule on the left and try to superimpose it over the molecule on the right, you can see that they're not the same, and it's also obviously seen over here, but they're not the same. So because that carbon is bonded to 4 different groups, it is chiral. Example 2, identify the chiral carbon of penicillamine, which is used in the treatment of rheumatoid arthritis. I don't know why there's a question mark there, but it should just be a period, probably. Anyways, just look for carbons, and I'll point them out here. You've got a carbon there, here, 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 and there. You might remember from the line angle formulas that the end of a line always signifies a CH3. Okay? So that means that those carbons are not chiral because they are bonded to 3 hydrogens each, which means 3 of the groups are the same. Okay. I'm going to rewrite them in because I need it for the next carbon right here. You can see we have a methyl group and a methyl group bonded to that carbon. So no, not a chiral center. Now the carbon right here has a carbonyl, an amine, and this carbon right there, which is not a carbonyl, it has the thiol and 2 methyl groups bonded to it. So that is a chiral center, and normally in organic chemistry you signify chiral centers with asterisks. And again, finally, the carbon right here, which I'm now writing in blue, is not a chiral center because 2 bonds of the 4 are to the same oxygen atom. So all in all, this has 1 chiral center, and it is just the one I've highlighted in blue. And I could write the asterisk in.